15 minutes version, I thought the next best thing is to do kind of like tips and tricks and things to avoid, things to be make sure you do in terms of the acquisition side and also the pre-processing side. So to boil it down to just four of the most pressing ones, I think I highlight them here. Some of them are maybe less well known to people who are processing like lower resolution data, but the first one here is to make sure your slice order is correct or what you expect, because when you have these really thin slices, the slice profiles won't be perfect and you'll get spin history effects. So I'll show you some slides of what that means afterwards, but that's number one. Number two is to be deliberate about the coil combination method that you use to avoid any artifacts, especially when people are interested in using the phase information, but also it impacts the magnitude as well. The last two are more related to distortion and blurring. So a lot of people so far, including Kurt, talked about how to optimize your acquisition for top-up, and I have a follow-up on how to optimize the actual configuration file that when you run top-up to make sure you're getting the best correction possible. The last one is eddy current correction, and you'll see more about that later. But this caveats here I pointed out, the first two are specific to the CMRR version of the sequence. We've tried quite a few different diffusion sequences over on the NexGen 7T, and the CMRR version seems to perform the best. It has all the bells and whistles, and the grappa reconstruction works really well. So that being able to use it to get the full extent of the first two are applied to that. And the second one, I just wanted to highlight again that if your data is blurred and not correct, if your data is distorted and not corrected properly across all of your time series, when you aggregate all of it in your final analysis, it's going to be just a mush. And we want to preserve the resolution, as everyone's talking about. We care about mesoscale. So just to give you that context before we get into it. All right, so slice order. So on the left here, I'm showing a plot of the slice index on the x-axis, and on the y-axis, it's the time. So the time from 0 to the TR, that's how much time it takes where you sample all of your slices. And what I'm trying to point out here is two different acquisition protocols. They are so similar. The difference is specifying 152 slices versus 156 slices. And for the CMR sequence, they are very clever because when you do multiband, you want to make sure like you have different stacks of multiband slices, and you don't want to have some at the interface between the two stacks. You don't want to have some different spin history effects. So they do this very fancy thing that depending on your slices and the number of shots and your multiband factor, the top one, if you have 152 slices multiband 2, that means the number of shots is 76. You'll get an interleave factor of 2. So then the time between adjacent slices is roughly half your TR. In this case, the TR is about 7 seconds. So each of these circles here is the adjacent slices will be about 3.5 seconds apart. If you went to 156 slices, you can see the interleave factor changes, and that means you only have maybe 2 seconds apart, which causes problems when you get spin history effects, calculate your TSNR, you get really bad instabilities. So this is again, in the case where you push the resolution, this data set was acquired at 0.9 millimeters, where you have some spatial overlap in the slice profiles of adjacent slices. So this is one very important thing when you're optimizing your acquisition. Okay, the next one is about being deliberate with your coil combination method. And for people using diffusion, back when we optimized the protocol from the Human Connectome project, the Sense one was all the rage because you get the right noise distribution in the noisy regions, especially when you go to high B values and you have really low signal and a lot of noise. The challenge is if you don't do it properly, you can get these dark pixel artifacts that I highlight in red. Compared to when you just do the default sum of squares one, you don't see that. Okay, so I'm not advocating for sum of squares. I'm just showing you what good versus bad looks like right now. So next is another step looking at where do those artifacts come from? If you look at the phase component of the image, you'll see that where you have phase singularities and phase discontinuities, those are the prime locations of where you might have those worm or dark pixel artifacts. And so when you go into the literature about where these come from, um, it's all about how you do your phase correction and combine all the coils that have different phase elements. So right into the next bullet point here. So this is a well-known issue. So there's been a lot of work over the years, including for QSM imaging, how best to combine your coil elements. This topic for the CMR sequence, it's come up at least since 2021. There's the GitHub for all the issues and requests for features on this GitHub website. And I just list a few here that to highlight. In 2017, they updated the Sense1 algorithm so that it properly generates phase images. So for people who want to do phase imaging either for fMRI or for diffusion, that's the way to go. Then people were wanting to have the phase across the slices to be consistent, and to have phase across the slices and consistent, it's better to use a 3D phase correction method where you correct the phase in the whole 3D. So they called that Sense1++. But there are still the black worm artifact. So in the 2025 release, the CMR team found out that if you turn off the coil compression and the noise decorrelation methods, you can reduce the black wall artifacts. But that's not the end of the story. So I followed their tips and tricks and compared the different versions of this thing, and I was like, I still get the black worm artifacts. So on the top here, Sense1++, phase and magnitude, you can see the phase singularities and the black worm artifact. So the point of this I wanted to make clear is that you should test the coil combination method for your setup. So your coils, your scan protocol, because it might not be as good as what other people get. So one cool thing about their sequence, the CMR sequence, is there's the MD advanced.ini file where there's a lot of customizations that you can do. And some of them are kind of secret, like you have to go to the GitHub or you have to ask Eddie Auerbach. It's like, do you have a parameter to change this? So it's not even in their manual. But yeah, I asked him, can you do this so that you can add a Sense1 parameter in the .ini file? You can set, if you want to compare the 2D phase correction versus the 3D phase correction that I talked about. And so this one is the 2D phase correction, and you can see the black worm artifact is gone. So yeah, just make sure you optimize the coil combination for your application. Okay, so before I get into the last two, I just want to do a quick overview, just a couple of slides of what the distortion correction methods are and why they're needed for diffusion. A lot of people here at least know fMRI, I would assume. And so on the left here, I'm showing susceptibility to standard B0 and homogeneity. Everyone knows about that. It was the top-up method that was talked about. But it turns out eddy currents also can cause distortion, and the field inhomogeneities that it creates can add together with the standard B0 inhomogeneities, and you get a total field distortions. And I wanted to show just a few slides of why correcting for eddy currents is important and give you a sense of where they come from. So in this example here, I'm showing for a diffusion gradient encoding of just on the x-axis, you get an observed image. And then if you correct it for all the distortion, you get the true one. So I'm going to flip between a few different diffusion gradient settings, and you can focus on this of what the image looks like and what it should be when it's corrected. So just take a look here. I'll flip through a few times. But what you'll notice at the observed image in the red box, you can see that the brain is jiggling around depending on what gradients in diffusion encoding is used. And you can imagine if you didn't correct for this, then your data is going to be all like blurred and inaccurately aggregated across space and time. So you really want to correct for both. You want to correct for B0 effects with top up, and then correct for these eddy current distortions with an eddy current correction method, which FSLs provides both. So here, for strategy number 3 that I'm trying to advocate for is to optimize your top-up config file for the spatial resolution that you're applying for. And interestingly, like over this U24, I had the chance to collaborate with some of the best labs in the world for diffusion, and nobody checks this stuff. Everyone uses the default, and I'm going to show you why it's important to not just use the defaults. But obviously, like for what Kurt showed, there's a lot of groups starting to do 2-way or 4-way phase encode acquisitions to spread all your diffusion directions across the different phase encodes. And so obviously you want all of those to be co-registered and undistorted when you combine them. So the default, if you went into this file here and looked at what are the warp resolutions that it iterates over to correct for this distortion, it goes from 20 millimeters all the way down to 4. So if you're acquiring like 1 millimeter or sub-millimeter, 4 millimeter warp doesn't make sense. It's like way too coarse. So then just a caveat, if for some reason you thought, oh, the FSL provides a 17 version, why should I try that? But it still goes to 4 millimeters. So they assume that you're still acquiring low res at 17, which is weird. But it's true, you need to account, it would be good to account for the lower spatial frequencies one at 17 because the distortions are also broader. So here's improved version. Of course, there's many more lines in the config file that people should look into, but this is the main one I found that helps. So I go all the way down to 1 millimeters, and I'll show you what that looks like in the next slide. So first two are without correction. Kurt showed this as well. So you can get AP and PA, and you use those two in the top-up algorithm to find the intermediate distortion, which is supposedly the true undistorted image. Then here's if you use the default config file. So I'll flip between these two. And you can see, well, it looks so much better than the original. But if you look closely, you see there's inconsistencies on the order of multiple voxel lengths. So if you use this correction, you're not going to get good mesoscale. So then when I saw that, I was like, what? This is not acceptable. So looking at the config file, if you do the 1 millimeter version, toggling between them, it's almost perfect, except for the fuzzy ripples. And that's one of the reasons why having both of these can also, when you average them, you can correct for fuzzy ripples that Renzo and Alex were talking about. So, but yeah, just be careful about your top-up correction. That was that slide about. For correcting eddy currents. So FSL is the standard. It's used on pretty much all multi-package, like all labs that I've worked with, they might have different analyses packages, but for the eddy, it corrects for eddy current distortions and motion. And it's so far no one's been able to beat it, so everyone uses it. So especially if you go to high B-value, strong gradients, they're going to have a lot of eddy current distortion. So you got to correct for it to make sure you're not blurring your results at the end. Turns out there's a lot of parameters that you can tweak on this algorithm as well. But there's two that I want to focus on today, and that is the first level model and the second level model, which all impact the spatial complexity of the eddy currents and how the model is, both mathematically and spatially. So if you didn't do anything special, if you just run eddy, it will use the defaults. So for first level mode, it will use quadratic. And for second level mode, it will use none. Okay, so let's see how that looks. So this is just an example. For shortness of time, I'm not going to go through all the possible permutations, but just to give you a sense how these options matter. So here's the default for a B value of 25,000, pretty high, but going to be very standard for a lot of our collaborators. And I'm going to compare it to if you use the HCP settings, which changes the first level mode from quadratic to cubic. And so that one you can already see some tangible effects, especially in the cerebellum, visual cortex, and frontal cortex. Okay, so that's comparison number one. Then what if we actually turn on the second level modeling for linear? Similarly, you have a pretty big effect. So key takeaway is to optimize. I'll go through all the key takeaways right now. So number one, verify your slice order and your coil combination. Make sure they're optimal for the scan protocol and the head coil that you're using. Don't assume the FSL defaults are good enough for your data set. Tailor your top-up and eddy currents correction settings for your scan protocol. And in the past, this package and correction tools have been out there for probably like 10 years by now. And back then they were like, well, we need to use the best model, but the minimally complex because of computational needs. But now like computers are like way faster, so there's no reason to just use the basic model. So when I ran those comparisons that I showed, they're kind of the same amount of time. So I was like, why would you do the poorest one? Okay. So then the last one is to check your data quality at the different pre-processing steps. It's kind of obvious, but like, and this is a good one for maybe at the end for Q&A and stuff, but Peter Basler's group, they've used some of the best scanners in the world, our scanner, the Connectome 2, at really high resolutions, but at the end of the day, they're like, look, the images look so crisp, but then after they go through the processing pipeline, they look like mud. So they can't see as much of the mesoscale as they would like. And of course, there's a whole list of possible reasons, but I just showed you a few, and those look pretty big deal to me. So just check all the processing steps to see if you can find easy things to fix and to make sure it's as good as you want it to be. And the last one, everyone knows these, the website for the NexGen 17 project and our email address. So I want to thank everybody for their attention and for all the team that made this project possible.